Ja. Vi fyller i de här matriserna lite grann. Vi drar oss undan. Och ett sånt förhållande bygger på något sätt.
Okay, so...
Is this on screen? Because I think this...
maybe that's too big.
Yeah, it's almost too big, because then the bottom part is missing, I think.
Can you change the resolution? The screen resolution?
Yeah, I thought it was flow at the bottom. Yeah.
That may be better.
Yeah, probably if you can see it.
Yes.
Okay. So, I'm going to talk about turbulence and instability on the data in general. There's work together with Philip Slatter and Arne. So that's something that we started not recently, but perhaps a year ago, half a year ago. And we did this calculation on the EGNO. So we want to solve some results from this one. So this is the case that we are looking at. So this model is very simple. So this is a fully developed channel flow. And this channel then is rotating along span-wise direction. So what a classical case. Many people have looked at this case. So what is known from previous studies and from low to moderate rotation numbers, then you can see that the turbulence is enhanced on one side and the dent at the other side. It has been observed in experiments and direct numerical simulations. But quite recently, about 2 or 3 years ago, Olaf Rundelstam in our group, he did some DNS calculations, but then now at much higher rotation rates, and he saw then that the turbulence, if it was damped on both sides in the whole channel, and if you then even increase the rotation rates, the channel becomes fully laminar in that case. So, but these kind
but would this also be true if the grain was not studied on?
yeah, it is.
Just maybe show again the geometry, because I was sure.
No, it's this one.
So the omega is the y-axis? No, the x-axis is the omega axis, or
x-axis is streamwise, one normal, and then this z is the spin-wise, and it's rotating in both spin-wise direction.
Yes. So the flow goes in the positive x direction.
So
Yes.
that was more
in the z direction, right? Yes. Isn't that right? Isn't that what it? Omega is equal to z.
so it's like that. And you flow in that direction. So it flows like that, and then it's rotating about this direction.
Omega is in x dash x.
Omega is perpendicular to the plane.
Omega is...
Right? The omega is perpendicular to the board.
So that is rotation x, and it's
So omega is perpendicular to the board.
So around it's around spin-wise direction. Then. So in fact, in this case, you can show that the rotation doesn't affect the mean flow. So if there wouldn't be any turbulence, and it just would be plain positive flow, even no rotation. Yeah. Okay. So this has been observed then. So at high rotation numbers, then yeah, at very high ones, it just becomes laminar in this case. So, and to understand the stability of rotating flows, we can perhaps look at the case of from uniformly sheared flows in rotating. Then it's rather helpful to look at this rotation ratio. So there's a ratio of the imposed system rotation and the rotation of the mean flow there. And then you get this parameter S. And then by several kind of theories and also RLT. You can show that rotation is enhanced or increased in turbulence if then it is between -1 and 0. And rotation damps and turbulence for all other cases. So, and then for neutral stability is then S is 0, so that's just non rotating case, and S is -1. So that is how then the rotation then roughly then works in this case.
So the really unstable case is the -1 limit, is that correct then?
No, what? Unstable, it is between these two borders, between -1 and 0. And in fact, the most unstable case is -1/2 about.
That's unstable, yeah?
Yeah.
Yes, right.
So, and then if you then look at then rotating general flow, okay, then it will look like more or less this. Later you will see that the mean velocity profile looks like this then, and then you can see that rotation is destabilizing in one side, so in the red part. You have a neutral stability here, and then you have then a stabilizing effect on the other side. So you get typical isometric profile for the mean velocity, also for the Rhino stresses there. So you have different effect on both sides, because then you have the ratio of the mean flow rotation and the impulse rotation difference.
So, I'm sorry, that symmetric one is the Poussin flow.
Yes.
And what's the
Well, but almost. It's this in fact what you will see later at very high rotation rates. It becomes almost parabolic and almost linear there.
Okay. And what's the other one?
This one you will see it later, but it's typically how the mean velocity profile will do that. I just want to point out that you have a different effect of then the rotation on both sides. You have one unstable side and you have one stable side each. So now we did some DMS. In the previous DMS, then the Rhino's tower was rather limited, was about 180. And what we want to do now is to look at higher Rhino's number, and then also for large boxes and then strong rotation. So these are a couple of the DNS that we performed, so quite many then. And then we fixed in the bulk Rhino's number, that's 20,000. And then in the non-rotating case, then you have a Rhino's tower about 1,000. But then it will decrease if you then have rotation. And in fact, at the highest rotation rates is 2.4. I haven't defined it. Rotation number. That is the bulk mean velocity. What was it? I was always think. No. What was it? 2 omega. Is that correct? Yeah. Yeah. That was it. So this and the rotation number. So the impulse and the impulse rotation and divided by the bulk mean velocity.
And that's what number.
Hmm?
And that's what's inverse.
Yes.
Yeah.
Yes.
Do you divide inverse?
Hmm?
Divide RO.
Yeah, that's a rotation number. So it's a bit confusing. That is how we use it usually. So then last means that it's fast rotation.
And RE tau?
Hmm?
RE tau.
That is
Is
the
that
friction
RE
minus number.
Pardon?
That is friction minus number. So you can then give many different minus number. That is what we use often for and this and the half of the channel width then. And you tell them it's friction velocity based on the wall shear stress. And this is the unit that we use often for wall-bound flows.
That's the Reynolds number.
So these are the mean velocities for different, the colors are a bit unclear then. But these are the mean velocity profiles for the different rotation numbers. Of course, in this fully turbulent for the non-rotating case, and then for increasing, so this blue one, you get an asymmetric profile, and you get a mouse region where the velocity profile is linear, and then you have the green one, a bit more rapid, and then this one, which should be a bit this one, 1.5, and 2.4 you can see that it's almost parabolic. So it opposes in the laminar velocity profile there. And in this case, then, where you have the linear region, then the absolute mean for Tessie is 0 then. So this is something not involved in the mean flow rotation.
Sorry, how large is Gaussian number?
The number is essentially the inverse of the rotation of
But they are not, in this case, the Rossby numbers are in fact not very small in this case.
From about 2.4. So it's about 0.2 or so in the largest rotation.
Well, the funny thing here is that the inviscid stability limit is rotation number equals 3. Then it will damp all the, that's an inviscid result where it will actually damp all the turbulence, all three-dimensional turbulence.
But you can also see that the rhinostraw for this case, highest rotation number is what T12, and the laminar, for the laminar channel flow is 300. So you can see that the rhinostraw is very close, it's almost laminar in that case.
So it's a quite high Rossby number then, so to speak. Even at a quite high Rossby number, relatively, you get laminarization.
Okay, there's a Walsh stasis then. So these are the Walsh stasis in a normalized, well, that's the friction velocities, and are normalized by the mean friction velocity of both walls. So this is then the friction velocity on the unstable side and this on the stable side. Then. And then of course if the rotation number is linear equal, so this one should be 1. And then if you have rotation then you see it increasing then. So you get a larger difference between the friction velocity on both walls, both the stabilizing and destabilizing effect of rotation. And then it goes down to 1 again, because the flow becomes laminar there, and in fact more symmetric. Becomes almost a parabolic rotation numbers. And these are the results for different calculations. So these reds one are my BMS and the black ones, and these are from the previous at low brightness numbers.
Sorry, I must. Why is minus?
Oh, this should be the rotation number. So that was a mistake. Yeah, that's correct. These are the RMS profiles, so this is for the steamized velocity fluctuations and the more normal velocity fluctuations. And then you can typically see that the run stresses become different on both sides. So this is unstable wall and this is stable wall. And you can see then you have the symmetric for the rotating case, and then if you then increase rotation, you see it first increase, then the peak here, and then goes down. But in this case, you can see that rapidly decrease in the velocity fluctuation. You have a strong damping effect. VRMS, this is all normal velocity fluctuations, you see that particular behavior then. So this is a non-rotating case then. And then if you then increase in rotation, you see that this peak from unstable wall increases a lot there. So you get a lot much larger or much stronger wall normal velocity fluctuations. And on the other side, on the stable side, you can see that it rapidly decreases. And at the high rotation numbers, you see that the fluctuation is very small there. So it's almost laminar-like in that case.
But when you get this laminarization, do you have any kind of 2D vortices splitting in the span-wise direction? Aligned with the rotation axis? I mean, if you have...
You get something later then,
Yeah.
with the instabilities. This is the production of turbulent kinetic energy, and here this is on the unstable side, and this on the stable side. On the unstable side you see that this peak is about 0.25 in normalized in wall units, and then it increases then with rotation A very high one, you just decrease again. Here you see that, if you compare that axis, you can see that you have a large decrease in of the production there on the stable side. What's also a bit interesting is here, so this line that is 0 there, so you get a negative, you have a small region at high rotation numbers where the production is negative. So then you have a transfer from the turbulence effect to the mean flow there. There's not so many cases where you have that, but in this case you can have it with rotation, with rotating channel flow.
That's noteworthy actually, because there are a few cases where you can observe spatially developing flows with strange inlet conditions and other things where you actually have transfer of energy from the fluctuations to the mean flow. Some non-stationary flows where you can also pump energy into the mean flow from. But it's a very unusual. Here it's a stationary case where you actually do have this.
But it comes from the Reynolds stress, clearly, right? Reynolds stress produces.
Yeah, it's where you have the maximum. You can say the maximum in the mean velocity and the zero crossing in the change of sign in the Reynolds shear stress are dislocated here, so they're not occurring at the same position. That's why you get this region there.
But isn't it that the length scale in the sperm-wise direction in the line with the rotation axis grows very much?
It grows, yeah.
So you get a kind of almost 2D turbulence there.
Right.
Yeah.
Yeah.
And in 2D turbulence you have a kind of an inverse cascade. So
Yeah, but it's isotropic according to that concept, but I think what you really have is anisotropy. So you have the Reynolds stress, certain components of the Reynolds stress which play a role, and such a thing is actually known to be generated once you have rotation. Once you have
yeah, but
rotation
you have the vortex stretching term, you have no vortex stretching anymore, and this will lead to kind of an inverse.
So in my understanding, the recipe number is not so small.
No, that's straight. Yeah, yeah, that's
So,
straight.
so the question is, how is the elongation in that direction? So the mineralization maybe not so
No,
strong in this
not
case.
true. No, I don't know.
But it is in some kind of, you can see it as some kind of inverse cascade actually.
So the rim scale in this section, this one, how large is it?
Well, at the end of all, also some movies that affect on the unstable side, you don't see so much of this case.
I mean, this is what is called lambda effect, which is it produces differential rotation in rotating bodies. I mean, like in the sun, you know that the sun is rotating faster at the equator than in high latitudes. That's called by a component of the Reynolds stress, which does not depend on the gradients of the velocity, but on the angular velocity in this particular case. So it vanishes only when zero rotation.
Well, another thing then, this was also interesting too. I've not only looked at the velocity field and the turbulence, but I also included a Pascal field. So I just both fixed concentration on one wall and the other wall, and then you get this type of kind of mean scale of files. So this is a normative case, and then here what happens if you have a rotation. So you get a very small, you have a small gradient here, and you have a very large gradient there on the unstable side. Yeah. So you get a completely different mean concentration profile. And what is also interesting to look at is at the turbulent bonding number. So that for just for normal shear flow, for scale transport and normal shear flow, this total bonding number should be about order 1. So that's a user assumption. But you can see that it just completely breaks down if you have some rotation. So even at the rotation number 0.50, you can see that it's here, this space, then the total bonding number is about 0.3, so it's much smaller than 1. And it goes down even more. And you have almost 0 there.
Oh.
Didn't find
Well, there's oops. So this is directly estimated from the computer from the DNS then. So that is then the so there's the eddy viscosity divided by the diffusivity, total diffusivity of the scale. Eddy diffusivity of the scale. And this is a total viscosity.
How do you estimate the eddy viscosity from the Reynolds stress?
That is directly from the DNS then. So you have just
So you measure the Reynolds stress and divide it by the
then
here?
Divided by the gradient.
and then you do the same for the scale.
So, if there is lambda effect, then basically lambda effect is being ignored to estimate the eddy diffusivity. Right,
That
actually.
might be the thing, yes. Stress is therefore reduced, even though UT, so this is something like the virtual UT. Journalist.
Okay, but yeah, something like that is really a challenge for turbulence models. It will not be easy to predict something like that. Will take of course.
I guess it simply means that this simplified, simplest viscosity type of thinking here, that just doesn't work for long.
Because there's extra terms.
They're extra.
Yeah, right. Which is also true.
That is exactly what we mean by lambda effect.
Yeah, but I'm a bit surprised that the effects are so large here. It really goes down.
Yes, and it's
becomes
even
very
the
small.
interior, throughout the entire interior. It's not just in one way, right?
No. Well, yeah, I only showed on the unstable side. So on the other side, he has more or less a molecular bit.
Just the right-hand side, yeah?
Yeah.
Yeah.
But here you can see it becomes really small. Then.
I'm sorry to be so troublesome, but in the direction of the rotation, what are the boundary conditions on the curve?
In this case, it's just in the direction of rotation homogeneous then. So we use periodic boundary conditions.
Here.
And also in streamwise direction. So it's only an inhomogeneous and wall normal. And there we just use normal molecular conditions. Then we look a bit about structures and kind of structures that you observe in rotation of wall. Quite funny. So this is what you see in on the stable side, very close to the stable wall there. This is what you see there at rotation number 0.45. You can see that yes, in fact, this region where the flow is more or less turbulence, and here, in fact, almost lambda. This is a streamwise direction, and this is spanwise direction. And this is a plane very close to the wall, parallel to the wall there. And it's very close to the stable side.
And you're plotting vorticity.
No, this is just the instantaneous streamwise velocity.
Streamline.
And then you really see this is a turbulence. You see the small scale structures, and you don't see any kind of disturbances there. So that is more or less lambda. So this is a bit typical. But if you
is it a full plane?
This is a full plane.
It's a full plane.
Yeah. But remarkable is that you only see it in the close to the to the wall on the stable side. If you go a bit further away from the wall, you can see that it becomes fully turbulence there. And on the other side, it's just 3/4 of the channel there is fully turbulent. It's only very close to a stable wall that you see this.
But if you would increase the box size, if this was possible, like the same, keeping everything else constant,
Yeah.
how would you expect the pattern there? It seems that the length scales are of variation here. The laminar turbulence is scales with the box, or is it?
No, it's probably this length scales should be more or less independent of the box in this case. So
Yeah, they should be independent.
in this case, perhaps it's a bit on the limit end, but
Yeah.
if you have very large boxes, then you would expect more of these bands.
Yeah, more.
This is what you see in very low, say, a transitional case.
Yeah, okay.
Great flow.
And without rotation, the spacing in span-wise direction is said to be 138 also. Wall unit.
Yes, for this near wall.
Near wall. And how the influence of the rotation on the spacing?
Oh, I don't know. We haven't looked at yet that.
Sorry, this is Y?
No, this is the span-wise direction.
Z. It is
This is Z and this is X.
X and Z.
Yeah.
So, but these small structures we see.
So the square
These are the. How many wall units do we have here? We have a lot of wall.
I don't know, but
units.
always this
Yeah.
kind of structure.
So these small bands, they have a. These are the traditional.
Yeah. So this kind of structure, they should
Yeah.
have spacing for about
Yeah.
100 plus units
Yeah.
in that space.
But the large structure doesn't scale with the.
So the whole box length is like 24, 25.
24H, 25H, yeah.
So it's a lot.
I don't know how
It's
much
very
it is.
short.
25.
No, this one is
3 pi, right?
3 pi, it's about 9H.
In wall unit.
Volume, I don't know, then you have to calculate it. I think the line of stall is about 600, so then you have to calculate it. What does it come? There's 600 times 9. 7,000.
It's a traveling.
It is probably traveling, yeah. I haven't looked at it, but it should be traveling. Another thing that we observed then, so this was at 0.45. If you're going to even higher than rotation numbers, and if you're going to look at the times here, so this is the wall shear stress, and URMS indicates the whole volume. And this is about rotation number 1.2. If you look at the time series, you see a bit mark of fingers improvement. So this is the time then. With the wall shear stress on the unstable side, you don't see so much. But if you look on the wall shear stress on the stable side, so the blue line, you see kind of peaks occurring then. And it's almost in a kind of fast periodic manner, you see these peaks occurring. So you see them always reoccurring. And if you look at URMS, so streamwise velocity fluctuations, integrate of the whole volume, and you see also large peaks there. So softening is happening there only on the stable side. And we have looked at also in here then. So these are the RMS profiles in all three directions. And so this is unstable side and this is stable side then. And the solid line is then during the calm periods. So that is at these periods. And then the dashed line is then during these periods when you get these bursts then. And then you can see that you have on the stable side, you have enormously increase in fluctuation. So during the calm periods, the fluctuation is very small, it's almost laminar-like. But then during these peaks, then you have a much increase in turbulence intensity. And this is not only for this rotation number, we see it also for the other case now. So this is for rotation number 0.9, 1.5 and 2.5. There you see this, all these reoccurring peaks there, in the wall shear stress and URMS. So we have some kind of instability, reoccurring instability there.
Do you know more about the bifurcation diagram? How this all? It must be an interesting bifurcation diagram. As you increase, for example, your rotation number, you must be an onset when you get this, or do you get it immediately at the onset of turbulence, or whatever? I mean, as you change the parameter further, is there a regime where you don't have this instability?
Well, I mean, if you go to very high rotation numbers, very close to 3, that is,
Yes.
3 you get, so you kill all the 3
Yes.
turbulence.
Right.
But if you look at the Navier-Stokes equations here, you can see that, of course, there are some motions that are independent of rotation. Those are the ones that are just the waves in beta equals 0, and the spanwise wave number equals 0. For those, they are completely independent of rotation. But if you look at the profile very near to rotation number 3, then you essentially have a parabolic profile. And then you can do the stability theory of that. And then you get the wave numbers that should occur according to linear stability theory. And those do occur in simulations also. And that's not too surprising, maybe, because you're so close to the parabolic profile. But the funny thing is that they occur and they grow non-linearly to a very high amplitude and break down the turbulence. And they create 3D turbulence. But the 3D turbulence will be damped by the rotation. And so it's damped again and until it gets very low, and then the 2D wave starts to grow when the 3D turbulence has low enough amplitude. Then that starts to grow and it breaks down and it does this. What Jack here has seen is that this also occurs for rotation numbers where you're really far away from a parabolic profile. And it's the same type of same kind of phenomenon at least, but you couldn't really do stability analysis for the parabolic profile because you're at rotation number 0.9 or even 1.5. You're far away from the parabolic profile. You have these two regions, you have some turbulence. So the more surprising thing is that qualitatively it occurs in the same kind of periodic manner at such low rotation numbers where you maybe wouldn't expect this 2D wave to grow actually.
But you have to do a further investigation what Reiners number do the equivalent just to make a map from what Reiners number, what rotation is. We don't know yet. So this was just one series.
Very high rotation numbers, this close to 3 again. You can also compute from the linear stability theory at what rotation number it should become laminar because it's slightly lower than 3 because of the viscous effect, the finite Reynolds number effect. And it just, of course, agrees perfectly more or less with the linear stability theory when the deviation from 3 in occurrence of the laminarization. But this is far away from 3, so this is in another regime, and it's still qualitatively at the same time.
Yeah. So these are some visualization, a snapshot a little bit before you have this large burst, and then you see what kind of structures you have. So in fact you have this kind of 2D waves there. So this is in span-wise direction, and these are the waves and close to the stable wall. So the other side just on the unstable wall. These are the wall normal, the velocity fluctuation, and this are streamwise velocity fluctuations. And this is in parallel and very close to the stable wall. This one is just a side view. So this is a wall normal direction. And here you have the stable wall. And the other parts, just unstable side, don't show because it is fully turbulent. So you have only these kind of structures on the stable side. So you have this kind of large two-dimensional waves, and these are, in fact, what Arne said, they are not affected by rotation.
So the red region is turbulent region, and the blue is laminar-like region.
No, this is just gives an idea from, these are just 2D waves.
That is, the previous figure looks like periodic, and the period is determined by some traveling pattern, or what is the determining factor of the period?
The wavelength? I don't know.
Well, I mean, that's what I say. If this would have been a higher rotation number, closer to 3, then you can compute the wave number that occurs there from your Sonnenfeld equation, and you get the damping and everything according to what you would expect here. And actually, you can also get some that are betas that are slightly different. Here you can see those and how those are damped and everything. But this is far away from 3, so this is a highly non-linear range, but it's essentially a 2D wave traveling through the box here.
Could you go over the previous slide? And in a non-turbulent period, how is the flow? Is it laminar-like or turbulent flow?
What?
In the, say, non-active period.
Yeah.
Is it laminar-like or turbulent? They float down.
It's quite close to laminar, but I wouldn't say it for this case. I think in all cases you still have some fluctuations there. It's not fully laminar. But in particular in this case, I think that even in the calm case, you have still quite some fluctuation there.
But essentially what happens during these peaks, I mean, it's a breakdown of the wave and generates a lot of 3D turbulence, and then it damps out, and you see more and more of the wave coming up, and it grows exponentially and breaks down.
You can also see that they are not perfect two-dimensional waves. You have some disturbance on it. So there's some noise there still in this case. So this was just before some this burst happens in, and then at some point the amplitude of these waves becomes so large that these waves also become unstable. And then what you then see then, you have to do some visualization, you see this kind of ladder-shaped vortices appearing on this waves, and then the whole thing breaks down and gets just fully turbulent. So that's perhaps something was shown in the these are more of these waves. I will skip that. But, can I show this movie somehow? So then I would conclude with the movie then, for one case. Or movie, just couple snapshots. So this and the streamwise velocity fluctuations on the stable side. You see now these two V waves occurring then, and then the certain moment it just become unstable and they break down. So it was a bit fast perhaps, but can I?
Yes, the specific.
Yes.
Yes.
How do you press? First you're going to see anything, but now you see 2D structures appearing. You see the waves, and they become then unstable then, and then they completely break down. What was perhaps not so clear then, I don't know if I can just click on one of these. I just wanted to show one of these pictures. Can I just do plus? Or?
Is this initial condition? This one?
Well, no. Well, this is during one of the periods, so it doesn't matter.
How long time interval did you see?
So this was just say before you had this burst and then beyond this burst. So there's quite a long time behind that.
You want one of these pictures, right?
Yeah. Can I also then? Yeah. Can I just go on?
Yes, which one?
I think perhaps 35 or 40 almost.
71?
No, say about 30 or 35. I think. Yeah, plus. Okay, so then you see that. Is it now? I think a bit further.
45?
Yeah. Okay, so there's this. A bit further, plus 50. Okay, you still raise then. Still before then really the burst happens. 55 days.
So what the odd phenomenon actually in turbulence and this.
Here you get kind of instability occurring then. So this two-dimensional wave becomes unstable. So if you go a bit further, see this instability even a bit clearer. So one further, just or 60 days. Okay, so this already then the instability already is present. You see the whole, you see then the occurrence of turbulence there. So then you get really dispersed. But what is also funny if you go a bit further then. So this turbulence will spread over the whole channel then on the stable side. You can see it. If you then look at, you see then full turbulence, but if you look then a bit carefully, you see some kind of, I don't know if this slide, but then after it breaks down, you see kind of this spinwise vortices going there. There's one further, but 67.
67.
In one of the pictures you saw some periodicity, fourfold periodicity in the X direction.
Yeah, there's no different here, but one of the slides you can see that you have then much smaller, but then you have more or less these spinwise vortices. Once these waves completely break down in turbulence, you see then in the turbulence, because of rotation, you see this spinwise vortices. And then this turbulence just decays because of the rotation. And the whole process can repeat itself. At some point, and the 2B waves will appear again, and you go again.
And what is the period?
It's sort of long then, so
Compared to the rotation period?
I haven't looked at it. That
Able to see it from that time frame.
yeah, but
Probably very low. I mean,
Yeah.
it depends on the damping of the turbulence. It has to be
Yeah,
kind
it's
of
quite
low,
a
so
presentation
it's not really a period that it's more or less not just determined by the damping.
So you have, is there a paper on this yet? The draft or something? Or
No.
No.
because then it was really
You had a paper in 2009 about.
so these are the time scales then. So this normalizing with the bulk mean velocity and age then. So that is it's not actually of the order of the rotation.
No, it's much longer.
It's much longer.
Much longer.
Yeah. But it is probably a bit related from the on the box size. It's not independent of the box size. So it depends on how many waves do you have in a box to perfectly fit into the box or not. Because then if you then I did also some yeah, these are calculations and with smaller boxes then you just have one wave then. You can see that the period is not completely independent in what you choose. So they're a bit different now.
So basically you have the linearly unstable mode, which is the wave, and that punctuated by turbulent events, right?
Yeah, if you take it to larger rotation numbers, then the picture becomes rather clear. Then you can sort of predict what's happening from linear stability theory until it grows non-linear, and of course then it's a non-linear phenomenon that it breaks down. But then you get the damping because of the rotation, and then it starts growing according to some of those modes that you see there, and those they are the least damped modes or most cyclic modes that you will see. But here things are so non-linear anyway. I mean, that rotation number of order just one here, you're pretty far away from a parabolic profile, and there is background turbulence, but there is still some kind of what seems to be analogous to this linear mechanism of the growing 2D wave.
You still have some reminiscent of the 2D wave.
Yeah, I mean that's independent of rotation number. That is independent of rotation, right? So it's so it's unaffected by rotation for V equals 0.
That will be one of the next thing that we do in apply a stability analysis then. So take the mean velocity from the linears then, and and then do a stability analysis on this profile. Is that the right one? And then see if that what it means what the doing is. But the other thing is that we want to continue this DNS, and but then on the higher ones number and probably bigger boxes, because we've got computation time on the UG in Germany. We've got a lot about 46 million core hours to calculation next year.
Can we make a note also here that, I mean, this is unobserved not observed in experiments, and then you would say, well, let's go down to the lab and do the experiment, but that's extremely hard to do actually. And now we come to the stage where you do simulations that are actually just practically impossible, or not impossible really, but it would require a major, very major experimental effort to produce these things.
Because of the high Reynolds number.
Yeah, and high rotation and high Reynolds number, which is very difficult to achieve in experiments.
Is the geometry similar to the Coriolis platform to know rotating channel? People are doing experiment on rotating channel, and I don't remember which.
There have been some experiments in Japan actually in rotating channel flow, but not that has been limited to very low rotation numbers. Then there was an experiment set up like 5-6 years ago in Canada, where they had the ambition to go to substantially higher. I heard from them, I kept in contact, and they got some very preliminary results, and then it became quiet. So, well, they gave up, more or less. I would say it was too difficult to do. But I mean, it's not impossible, but it's a really very demanding kind of experiment to do actually. So, but here you can now do it quite through simulation.
What kind of sizes are we talking about for a physical experiment?
The problem is that you have to have a reasonably large, number of meters anyway, a channel, and it has to rotate at frequencies that are at least hertz or 7 hertz, and then you start to get g-forces towards the outer edge of this that are very large. So we had some plans here actually some years ago, but it's also after estimating all the effort these things have to do. We concluded then, I remember, that we had to encase it. We had actually a bunker really below our present wind tunnel, where you would have concrete thick walls around, and for safety reasons you would need something like that just to, but it's still, as I said, to obtain this, it would be extremely difficult and costly to do it.
An interesting case will be then a curved channel flow. And we get something similar. But I guess in the curvature should be very curved to also this kind of instability. So I'm not sure that it's possible to do.
The curved channel flow might be somewhat easier to do, but even that would be fairly large. And we'd probably have to do it in water to get sufficient rotation and
Maybe you need to change your fluid to liquid helium.
well, that's
Not superfluid, but just liquid helium.
Or even fluid helium. The largest, or the next largest Reynolds number experiment on pipe flowers, towards experiment.
the problem
The
is
pipe
that
is 1 centimeter.
yeah. But you won't get any. You can do the experiment, but you won't get any measurements from
No,
it.
I know, that's very difficult.
You can maybe realize the flow, but you won't be able to learn anything from it. That's the problem, I guess.
But you can maybe measure such things as the wall, the total wall shear stress and things, average quantities.
Now they will put kind of particles in EM.
You do? Good point, yeah.
And
You have problems with the refraction index changing, the
yes, but
temperature.
I think people are working on that.
Yeah.
Some results at least.
Yeah, but there's still no huge problems.
The numerical experiment is easier here, but it's come to the stage where in some cases it's actually easier to get higher up in Reynolds and rotation numbers and all that through numerical experiments than physical experiments today. That's,
So not
so
easy.
funny.
That's impressive. That's the opposite problem. They can't quite believe it.
But this supercomputer that you have time, what is it called?
Eugene.
Yeah.
Somewhere in Germany, I don't know.
Yeah.
Jülich in German.
So what is the
It's very small
capacity
processors.
of this computer compared to our?
I don't know, we have to, we're just starting, so we have to test it. But then probably we do calculate up to 16,000 cores. At least we need to do that.
Is that in your code scales?
Hmm?
In your code scales?
Hopefully, but that should be possible. It's a blue gene machine, so that is very good communication.
I guess it will depend on your transformer. I mean, how parallelizable the Chebyshев is essentially.
Well, yeah, it's spectral, so it's, well, you know, it's not so easy to parallelize.
Yes,
It's quite difficult to get good scaling. And,
How high is the sustained performance as compared to peak performance?
It scales there. I mean, what Philippe here showed that it scales extremely well on the new Cray here to 16,000 cores. So,
but then it depends on the number of nodes there. So I only see this very good scaling on very big problems there.
But scaling this operation is not good.
Yeah.
So, as compared to peak performance, how is the sustained performance?
I don't know for this kind of,
10% or so is big.
I don't know what it is for the blue gene. I don't know. I guess it will be something, for this machine it will be something like 10 or 20%, not much more I guess. It's not like a vector machine that you get 40-50% of speed performance.
Yeah.
So it's much lower there. But, well, the machine has 60,000 cores, so that is the good thing.
60,000.
Or many more, but we can run on max, say, 16,000 cores.
for this base project that we
16 or 16?
16.
16.
16,000.
So it has more than 16,000 cores.
The machine, yes, but there's a
Yeah, but
Yeah, but
we
you
will
have
run it, we will run it up to
Yeah.
16,000, but it has, and that will be like the force of the machine or something like that.
or even less, I guess, but then I guess one machine has perhaps 200 or half a million